So our project was on corrosion prevention in the marine environment. It was written by the four of us, Aiden Curley, who was our research facilitator, Kayla Huynh, which is me, the team facilitator, Connor Kelly, the product manager, and Jack Bao, team manager. So an issue that our team faced was finding a meeting time that fit with all of our schedules, considering we had different times for classes and not all of us live on campus. To counter this issue, we made sure to communicate plans well and, according to our agreement, follow up on every single meeting time. For our potential thesis, we have one, store petroleum in cool areas with fire retardant and away from engine combustible areas. Two, use natural gases as fuel to help with fuel efficiency. Three, use chemical coating on ships to prevent sea life from attaching and growing. Four, use chemical coating to protect against corrosion and use a chemical agent to treat corroded areas. And number five, filter water through a chemical process and store in a clean compartment that prevents corrosion. For our final thesis, we chose to research on chemical coatings to protect against corrosion and ways to treat corroded areas. We chose this thesis because it was the most generalized and covered all of four of our different respective fields. So for our mission statement, our purpose of this project was to extend the usability of ships and implement innovative measures to prevent corrosion. Through advanced materials and extensive knowledge in chemistry, we are looking to enhance the longevity and efficiency of maritime vessels, contributing to a more durable and sustainable maritime infrastructure. The first location that we decided to take note of on our boat trip was the Pelican Island Causeway. When boats go past this part of Pelican Island, the bridge will raise up just to make sure that the superstructure of the ship doesn't break. The bridge goes beyond the ocean, and the evaporation could cause the seawater to corrupt the inside of the mechanics. So electrical engineers might need to write a standby system to reduce the traffic damage caused by those potential problems. The second location that our group decided to take note of was the Galveston Causeway Railroad Bridge. This bridge is much bigger than Pelican Island Causeway, which means raising this bridge will not be a good method. It's not efficient. It cuts off busy traffic. The road and the gate are independent, which means that boats and ships can come through, and the gate will rise and prevent traffic buildup. To create a system like this, civil engineers need to create a strong and sturdy structure in the middle of the ocean, while also protecting against saltwater corrosion. Our third location is the SS Selma. This is an old warship that has been exposed to air and seawater since World War I. The whole ship is corrupted by seawater, and it's very visible to see on the ship's body. It's made of concrete and metal, so it's very susceptible to corrosion, saltwater corrosion. Material engineers and chemical engineers need to find better material to slow corrosion processes so that we don't end up with ships like these. Our fourth location is an ocean oil field. The Galveston Ocean Oil Field is located close to the island, extracting oil from the ocean. Petroleum is the main energy resource in small volume and high energy capacity, but it causes a certain amount of pollution. And our last location that we decided was important was the Galveston Sulfur Plant. Our fifth and final location on this PowerPoint is the Galveston Sulfur Plant. It's a pile of sulfur that is exposed to air and forms a chemical reaction forming sulfur dioxide. It pollutes local atmosphere and it affects local vicinity.
Finding which related to the proposal the most. Location that related the most to our proposal was the SS Selma. Like metals, the concrete on the ships are prone to corrosion. This relates to our proposal because our topic has to do with corrosion prevention to prevent corrosion on ships and to therefore increase the longevity of the maritime business. What is the scientific information from the literature? The resources gathered from our sources provided scientific information on the solutions to help prevent corrosion. From our sources, we have learned about three main ways to fight corrosion, especially in the ocean and coastal environments. The first method is using paint to protect metal from corrosion. The second method is using a metal less prone to corrosion to protect the main metal that is more susceptible to corrosion. And the final method is using a process called cathodic protection. Method 1, using paint as a protectant. The scientific field that applies to this method is both chemistry and chemical engineering. Their approach to this method of corrosion prevention is to use a special type of paint coating to create a layer protectant on the metal. The specific type of paint that coats and protects the metal surfaces from the corrosion contains a complete mix of ingredients. These ingredients include the cross-link organic polymer binders that help glue the paint to the structure it is applied to. This is according to Futurum Careers. This problem affects the marine environment in the area of ships and maritime business, but not the environment itself. Engineers should handle this problem by using the method of protectant coatings to create a layer of paint that protects the metal from oxidation and therefore corrosion. Our idea to overcome this problem in this method was explained earlier, which is also promoted upon by Professor Stuart Lyon and Dr. Yanwei Liu. Professor Lyon explains that we can prevent the water and oxygen from interacting through the applied paint coatings. They also explain that the paint used can act as an electrical insulator to slow the electrical chemical process of corrosion. This is also according to Futurum Careers.
The second method we came up with for preventing corrosion is to simply not use a material that corrodes or a very corrosive prone material. While we were on a boat trip, we came across the wreck of the USS Selma. The USS Selma has been there since 1920, and for the most part is in reasonable condition, unlike the SS American Star, an ocean liner from the 30s that was wrecked in the 90s off the Canary Islands. As of 2020, there is really nothing left of the American Star apart from a coral reef. USS Selma, however, stands loud and proud today. And the reason why is because USS Selma is constructed primarily out of concrete. Concrete is a material that doesn't corrode, unlike the American Star, which was made out of a traditional steel construction as she was an ocean liner. The problem, though, is that iron is huge in our world. According to a National Geographic article, the world produced 1.864 billion metric tons of steel in 2020. Now, steel is primarily composed of iron, and during the electrical and chemical oxidation process, iron corrodes in iron oxide. Iron oxide is a useless powder that just flakes off and ruins the structural integrity of steels and other iron alloys. Now, the reason that this is such a problem is because iron is in the list of the top 5 most used man-made materials, meaning that in marine environments where corrosion is prevalent, iron is a very big problem. Now, one of the simplest methods is just substitute it out. However, substitution is hard. One of the easiest metals that we could substitute it with is aluminum. According to a US Geological Survey, aluminum is one of the most prevalent, in fact, the second most prevalent metal in the Earth's crust, just underneath silicon. The problem with aluminum, though, aluminum doesn't like to be welded primarily, and it takes a bit to get it out of ore form. That's why aluminum has generally been relegated to aerospace and aircraft usage, because it's a hard to manufacture but extremely lightweight and robust metal. Now, as of the 90s, a new technology came out called friction stir welding. Friction stir welding allows for the easy, safe, and environmentally friendly, cheap way for aluminum to be welded in large quantities. As a result, aluminum is now entering the market as a completely viable and useful replacement for irons, as aluminum is not only lighter, it's stronger, and it doesn't corrode like iron does. Aluminum does corrode, but it forms a thin top layer very quickly, and it doesn't continue in the corrosion, unlike iron, which is slowly eaten away. For this reason, the method of substitution for aluminum is an extremely viable replacement and an extremely viable method for corrosion prevention.
So electrochemists found out that the corrosion process is highly related to the loss of electrons. They thought that controlling the direction of electrons might slow the process of corrosion. One of the methods they found was cathodic protection. This slide talks about how we use cathodic protection, letting the sacrificial metal lose electrons rather than the metal we want to protect. Engineers use the metal with a high reactivity as our sacrificial metal. Connecting the protected metal with the high reactivity tend to lose electrons faster. Because of this, the anode side, which is the sacrificial metal, will be ionized, and the electrons will go to the cathode side, which is the metal we want to protect. Since the cathode has a sufficient amount of electrons, it will corrode slower than without using the anode. Those two pictures are great examples of the practice of cathodic protection. In many cases, the body of pipes and the ships are made of copper. Because of its low price, and the sacrificial is in high concentration of copper ions in soil or seawater are toxic to plants and animals. So protection from corrosion becomes essential. Under the use of cathodic protection, zinc has a higher reactivity than copper. In other words, zinc loses electrons more rapidly and corrode faster. Instead of replacing the entire cathode, workers can install a new anode after corrosion has occurred. This technology has been widely used because putting in new sacrificial metal is cheaper than replacing the whole pipes and the sheet.
Here is a list of our references. As you can see, we have plenty, and that concludes the presentation.